В последния си
Да.
да видиш дали ти е изписано името, дали се вижда зума.
Да, вижда се. Само да, айде се пише. Сега ще го вдигна малко само да се вижда, ако се наложи целия окей. Добре, да, айде са, добре.
Да, и се върни обратно към
Y me di cuenta de una cosa, ayer que ya lo había hecho, pero me he dado cuenta, que en dimensiones bajas, 13, medio superior, la localización está en puntos fijos y
congratulations.
oh,
Have you seen my message? No? No, I sent a message on your phone. SMS. Yesterday evening. SMS message on your phone.
No, because I don't have.
You don't have a roaming?
I don't have roaming. I have a Bulgarian SIM card at the moment.
Oh.
So I didn't get the message.
I don't know your Bulgarian phone. I don't know. It's a secret.
Well, it's not even for me. Even.
You went to your...
Yeah. No, I didn't get the message.
This is your phone actually.
Yeah, that's my phone. I get the message once I get to Mexico.
Oh, yeah.
Yeah. I didn't get the message. So. What's the text of the message?
Правили рекординг или само стриминг? Без рекординг, окей, добре, айде чао.
Oh, sorry. I'm very happy.
You obtained officially a letter to get after the They finally managed to get it on Zoom. They did decision, then the decision will be approved by the advisory board and then it will be
I'm extremely happy.
Now we can start the discussion of when it is possible for you to start the This is one issue of the mathematical which was sent to this address. But
these are the one word to begin with in English. And it doesn't have the school.
So you can send me the address which will go to correspondence.
This problem is that it doesn't have a split entity. So, yeah, there is no way. My phone problem.
This is the official address which is put on the website. That's your address. They just copy it. So you can open it. And even if I can give you the other issue, because I sent to simply not to send anymore. If the address is not working, no need to send by post.
I'm too early.
Yeah?
So because, you know, for example, if you send a paper, she asked if you need to have the paper. And I have never gotten it. But it's maybe because I don't know how to use
The system. Okay.
So
you can make a meeting.
Yeah, I will explanation. 15-minute explanation. The principles how to go about it would help me very, very much.
Okay.
But I don't really have to celebrate a little bit. It's kidding. This is fantastic. It's great.
So when are you ready actually to officially start?
Well, I have to. I mean,
It's necessary to finish the academic year in Mexico, or you can start as an answer. For us, it is better to start as early as possible.
April
Yes. If you can
Even
start
easier.
from 1st of April,
we only have 7 talks today. We have, you know, I don't know about
Всичко наред ли?
Да.
Да, верно, вас го казах, че един ден той ще отсъства.
Да.
Съвместно.
Без да ме хвана.
бъдеш възнаграден. Какво си казал ли?
Да, говорим. Имаме си...
You are going to tell us what it's about.
Exactly. The cyclic is the action of a cyclic. I tell the next will say, the next will say, and the last one. Pues ni siquiera ni contigo, ¿no?
All right, good morning everyone. So we continue our marathon in topics related to atoms. So let me just use this opportunity to remind you that there is a conference dinner tonight. It's a new restaurant. It's in the center of the city, just across the main building of Bulgarian Academy of Sciences, and Zeros. So it's. Unless you can sit here, I'll just move. For you, anything. So, I'll give you the address, but the reservation, if I'm not mistaken, is for 7:30. PM, and of course, as usual, we'll be on time. In any case, so for Bulgarian speaking, people, this is exactly the place which is can be described by a poetic name, Gazin and Cornea. No, точно там се намира ресторанта. But I mean, I will give a little bit more information later today. So now it's an immense pleasure to introduce Bernardo Uribe from Barranquilla, the city that is known as the city that produced Bernardo and Shakira. So, Bernardo Uribe, who is going to tell us about some very classical subject like Bogomolov multipliers and obstructions to rationality, but from new perspective. Bernardo.
Ludmil, thank you very much. Thank you very much for inviting me here. I'm very happy to be here in Sofia. Thank you for the organizing committee. So, I will present some sort of trail that I've followed, somehow trying to get some idea of some classifying spaces of certain actions that I was led by studying equivariant K theory that led me to study Bordism and that led me to think and to try to relate to some constructions in algebraic geometry associated to varieties coming from groups acting on representation or acting on vector spaces. So let me just start the talk telling you about the one of the questions in boardism, whenever you put a group acting on manifolds, and I will restrict myself to the case in which the manifolds will be endowed with a almost stably, almost complex structure, because not only because it's a little easier, it's also because it's related to complex geometry. So the idea is that in order to think about complex manifolds and the boardism question, one way to do this is to somehow relax the complex structure condition and to make it stable. So we'll say that a manifold that has a unitary structure, the tangent bundle after stabilization would be made complex. So it's not like a stably almost complex structure. So these are the manifolds that I want to study. And then I want to study the boardism questions of those manifolds when a manifold of that type bounds. And I'm going to put an extra decoration, which is I'm going to make it everything equivariant. So the question is, what is the boardism groups of these types of manifolds? So it's just a little drawing. Of course, this can happen also in a background space. So these would be the boardisms living on a space X. And these equivalence classes of manifolds by the boardism relation will define a set. This is the set of n-dimensional manifolds with a G action that is unitary for the time being. Everything is unitary, although there is no correction. The disunion makes this into a group, and of course, if you put them all together by dimension, then you have a graded group, that is this graded boardism group. And of course, you can do the Cartesian product of manifolds, and then you have a ring structure on this graded group. Very fantastic result by Tom, coming from Pontragin, is that these boardism groups could be obtained as the homotopy groups of a specific spectrum or a specific limit of spaces, which are these Tom spectrum spaces or Tom spaces, which is simply you take the Grassmannian and then you take the universal complex vector space over the Grassmannian, you do the one-point compactification, and then you beta manifold into some complex space, and you take the normal bundle. Anyway, you do all this construction that is due to Pontragin and generalized by Tom, and then you can get these groups as some stable homotopy groups of some space. This way, one can change this geometrical question of finding boardism manifolds into some calculations into homotopy groups. So this is the very beautiful and classical result due to Milner and Novikov, which is that the boardism ring of manifolds that have this almost stably complex structure is given by simply this polynomial ring on these variables, each one of degree 2, degree even, sorry. And these objects there could be obtained as a specific linear combination of some hypersurfaces that are called Milnor hypersurfaces. But if you tensor with the rational, you can get the projective spaces as generators. Now, the point is, if we know this, the question is, what can I say about the same question whenever I put a group acting on the manifolds? Knowing that I have this very nice, beautiful description on the case that I don't have any action. So the idea is, when you do this, then you get a homology theory, and the idea is to study this question using this structured homology. So in the manifold case, we saw that you can do this top-Pontragin construction, and you can think of the geometrical question by finding the homotopy groups of some spectrum, and you could try to do the same idea equivalently, namely you can just do the same type of universal construction. And this was done, Tom Dick, in the 80s, the 70s and 80s, which is simply the same idea. You take this object there, it's just simply the classifying space of free unitary actions with equivariant G, namely to take all possible representations, you put an infinite number of times, you take the Grassmannian, and so that's the Grassmannian on the right hand side, you take the universal bundle over it, and you can perform the same type of idea before, but you need to make sure that you find all these homotopy groups whenever you run over lower representations. That's somehow the stabilization procedure that you have to do in order to define the appropriate homotopy groups. And then these are the homotopy unitary equivariant groups obtained in this way, and this gives you some cohomology theory. Now, the previous tone contracting map that is done at the manifold level, of course, one can do it also here. You have a map of homology theories. Whenever it is not equivariant, it becomes an isomorphism. In the left is geometrical, in the right is homotopical. But in the equivariant setup, on the left-hand side, we only have positive degrees objects. Manifolds are positive degree. But on the right-hand side, because of this stabilization, we get a lot of elements in negative degrees. And an example of them is simply the Euler classes of representations. The Euler class of representations will be in negative degrees. And therefore, well, the map that we wanted to somehow to use in order to find manifolds up to Bordism, when we see it on the right-hand side, we don't have an isomorphism, and we don't even know whether this is injective or not for general groups. It is known when the group is abelian that the map is injective, but for general group, it's not known. It's known that it's injective when we tensor with the rationals, but the torsion is what somehow is interesting. So the idea is to understand that unitary Bordism ring when it's equivariant, but as a ring is very difficult to get a hold on it because of this formula group loss is very complicated. So one way to start looking at it is, well, since the Bordism ring is a very nice free algebra, first concentrate on the question, what is the structure of that object as a module over this nice polynomial algebra? So that would be the first question. And after some calculations on simple groups, or small groups, abelian groups, then it was detected that the equivariant group was only lying on even dimensional generators, and that the object was a free module. So if you think of it, that does mean that only even dimensional manifolds are not cobordant to the empty set. All odd dimensional manifolds with a group action are cobordant to the empty set. And also that it's free, there's no torsion in these things whenever the groups are. So this is
you spelling this name. You're very careful with Comenzane, even the accent is there.
Should have.
But it's Lazarev, not Lazarov.
Lazarev.
So which is Russian, not Bulgarian.
Sorry. I should change it.
Yeah, but and here, but so okay, free, but so what are the generators?
Oh well.
So how hard is this, sir? So
well, it's very hard. It is
S1.
Well, no, S1 is already hard, but S1 you can do it with.
We know it.
Yeah, Hattori did it in 1980s when he was trying to get the toric genus, and he started to construct in the generator. So that for the circle, it's a construction that is inductive for the generator. So you need to start finding sections for all possible actions. But yeah, in that case, just one circle. You put two circles.
Circle is already hard.
Nobody has done it, so I don't know how to do it either.
There's no product or anything. So because it's.
So this is all algebraic in some sense. This is all using projective generators. So it's all algebraic that you know that there are sections, but there are other things to give me exactly the generators. So it's an algebraic proof so far. So I don't know the generators for products of circles. I know the generators for one cyclic group. If you give me the product of two cyclic groups, I don't know. No, I don't know in the literature. It's not that I don't know. In the literature, it's not there in the literature. So this is a very good question to ask. What are the generators? And yeah, if you think about it, it's somehow it's not free action. No,
but sorry. So you just say it's a free omega star.
It's a free module. Yeah.
Module, but it's also an algebra. So it's an algebra.
Yeah, it's also an algebra, but as an algebra, it's also known for cyclic groups. Well, Igor, Chris, and for who have done some that they are there. I don't know if they're correct or incorrect.
And for the circle?
For the circle, the ring structure is also not aware. No, it is no. It's because of this formal product on the Bordism ring that has elements in all, so it becomes very complicated to track down all the possible. You use the product two-line bundles and you get all these elements in all possible dimensions. So that's very complicated to keep a track. So for cyclic groups of prime order, then there is something done by Igor Chris, but in general, there is some argument by Igor generalizing it to any P group that is cyclic, but yeah. It's more complicated than one might think because of the formal group law. So this led in the 80s to simply say this is a conjecture. That doesn't mean that it's correct, it just means that it was an idea that for any group, these equivalent Bordism groups would be free, and even dimensional generators, as in the case of cyclic groups. But somehow this turned out to be a complicated question because, as you can imagine, it depends on explicitly finding these generators and to find exactly whether there's torsion or not. So even though there are big machinery in the equivalent homotopy universe, this machinery is not suited to finding this question, which is very somehow geometrical. So I'm just putting some quotes of people that did it in the 80s, in the 90s, on which they said might be yes, might be no, who knows. And when we end up somehow looking at this problem some 2-3 years ago, and this Landweber, the topologist, he's very keen on talking to people that work in this type of questions, and he contacted us and he told us, oh, very nice that you're bringing to life this whole problem. So let me tell you why somehow we try to understand it. So what I'm putting here, and this is again, please don't take me completely, but this is somewhat related to what Kontsevich called symbols in the equivariant set. He's talking about symbols and atoms, so these are the symbols part. Symbols part means that I have a manifold with a G action, and I want to understand what is it on the Bordism group. And what I do, what one does is, well, look at the fixed point set and see it at the normal bundle. And the normal bundle will split by the representations that I did here. It splits in the representations, and try to, if you have a Bordism on a manifold that is equivariant, well, for sure you will have a Bordism of these fixed point sets. So the idea is you simply map your manifold to the fixed point data and the normal bundle, and then you can classify it by the universal bundles on the right, given by the representation, and every Bordism here will give a Bordism there, and this is a Bordism of very nice Rosmanians, and this is all even dimensional and free, so this right-hand side is pretty nice. So if we could somehow show that this map, putting all possible subgroups, would be injected, then we will be somehow done. So the idea is, if you localize the map, and in what sense is similar to what Kontsevich was saying, well, if you take your fixed point data and these eigenvalues that he was talking about, it's somewhat like these normal bundles that appear here, but I'm not diagonalizing them, I'm keeping the whole bundle as it is, because of course this is not a billion groups in general, but if it were a billion, I could just simply take one-dimensional representations. But I'm not putting the billion case here. So, and this is somehow the information you keep of your manifold, the fixed point data. So if you put all these things together and you localize the manifolds on all possible subgroups, then you have a map to the fixed point data. All these Rosmanians are there, and whenever you tensor it with the rationals, this is a generic statement that I will say in a second, it becomes an isomorphism. So, if you want to understand the free part of this equivalent Bordism ring, you can just do it by the fixed point localization formula, and you can just go and understand what is the non-torsion part of it by the localization on fixed point data. But the point is, how can I show that that map is injective? Because if it's injective, then I'm sure that it will be free. So one thing that one should look at it is, well, I could take manifolds with 3G actions. And if you take a look at the Bordism group of the manifolds with 3G actions, this is a lot of torsion. It's a lot of torsion because you can think of it, you have the spectral sequence of Bordism, and you can see the homology of this classifying space and the homology of torsion. So all these elements here that matter are torsion. Since they are torsion, and you can take a manifold and send it to manifolds without any restrictions on the action here is free, the action here is not free. Because the elements here are torsion, whenever you see them there, if these were torsion free, then they would bound. So what I'm saying is, if these were torsion free, any manifold with a free action would bound. So the question was, well, if this conjecture is true, then all manifolds with free actions would bound, and that's somehow key, like a small question that one could ask. All free actions would bound equivalently. If that's the case, at least we are sure that this will work. So the point is that this conjecture or these types of studies are known for very, very, very small types of groups, mostly a billion, and little tweaks on a billions. In general, it's not known. So I started at the beginning to try to show this in general. Of course, I failed. So I thought myself, well, instead of trying to show this on all generality, let's do it like they did it classically. Let's do it dimension by dimension. Now let's do it dimension 1, dimension 2, dimension 3, and if we can do something there, perhaps it will go to somewhere. So it turned out that if one restricts the question only to two-dimensional manifolds with free actions, and do they actually bound? Well, former student of Ernesto, that is now a professor in Oaxaca, started asking this for some groups, and he actually showed that for abelian, symmetric, dihedral, and some other groups, they actually bound. But a person working in low-dimensional topology, without noticing, showed that groups of odd order whose Bogomolov multiplier is not 0, then they don't bound. So there are surfaces with free actions that will not bound equivalently. So when we saw this, then we noticed, of course, that we could generalize it for any group, and then we put it in the machine of Bordism to see what it meant. So what I'm trying to put here is a short-extent sequence. Imagine, well, I'm now changing to oriented manifold, but the unitary case is very similar. So you take the unitary, the group of oriented manifolds of free actions, and these are three-dimensional manifolds on which you can have any possible subgroup in the middle as a isotropy group, but whose boundary has a free action. And you can take here the boundary map. So the idea is, I want to see whether this is surjective, namely any manifold bounds. So it turns out that the co-kernel of this map is precisely the homology version of the Bogomolov multiplier, which is, in terms of homology, is to take the second homology, namely things surfaces with free actions, and you divide by the ones that are coming from abelian parts, namely maps from the torite to BG. This generates some subgroup, you take a quotient, and whatever is left, these will be manifolds with free actions that will not bound. So that means that there is some sort of torsion in this object, which, as you can see, because you're killing all the abelian information, is a non-commutative object that matters, and that's what's somehow surviving. So then, since we know that this map that localizes the fixed point data is an isomorphism rationally, then the torsion, the integer torsion, this is more torsion at the second level of surfaces, is given by all these Bogomolovs. And since this is an equivariant construction, we need to take all the Bogomolovs of all the line groups. So you should somehow focus only on the whenever case equal the identity. And nevertheless, you need to put all possible fixed point data, and therefore it turns out that there is a lot of torsion in these equivariant groups, and this is only at the level of surfaces. It's only at the level, so we don't know what goes on after. But this somehow, because the appearance of the Bogomolov told us that well, we need to see what's going on in algebraic geometry to see if we can get some ideas on how to continue. Just to give you an example of a group whose Bogomolov multiplier is not 0, this is the smallest group, and it's as isoclinic class. This is 1. You could think of it as just a quaternion, something acting on C8. Cyclic group of order 8 has automorphism group C2 plus C2, and Q8 there is a surjective homomorphism to Z2 plus Z2, and this is it. So you just do it, and the whole idea that goes on is that there is a Riemann surfaces of genus 2 that somehow is, you have a map from these Riemann surfaces of genus 2 to this group, and that's the non-abelianity showing up there that is not obtained by a torrent, and then you just do the Hochschild spectral sequence and you calculate, and it's precisely Z2, and this is just one group on which the Bogomolov is Z2. How is this done? It's done nowadays using GAP. You just do it in the computer, and then once you know that it's not 0, then you can easily show that it's not 0 with the spectral sequence. But to look for groups whose Bogomolov is not 0 just by hand, this would be very difficult. Of course, Bogomolov himself and Salman, they showed some groups, but they were too big. These are the smallest ones. Good. So this conjecture is in general false, but that doesn't mean that we are out of hope. So you could think, when is the conjecture true, and what can you say about the geometrical version, the homotopical version, the covariant and contravariant version? So let me just give you some sort of quick look at other cohomology theories on which this problem has also been studied. So let's just think of cohomology theories which are complex-oriented. Not all cohomology theories are complex-oriented, so these are the ones on which somehow you can think of it that there is some sort of complex structure around them. And the ones that I'm going to care about is MU, which is unitar, which is unstable, the Brown-Peterson, which is a localization, and the Moravaki theories, which is a smaller version of the Brown-Peterson. So in the end of the 90s, and this was a study, and even though the homology of a finite group is whole torsion, and the homology is whole torsion, when you look at it at the K-theoretical level, it's completely free. It's very nice. So it turns out that whenever you take cyclic groups and you take the Brown-Peterson homology, which is a localization of the unitary Bordism ring in a prime P, this is a very nice proof of Landweber. Not only that you have Kunet, but it's also very much free. The cohomology, the Brown-Peterson cohomology of cyclic groups. So completely different than you might think as in singular cohomology. It becomes a very nice object, and this is the formal group law here. So this is somehow telling us, then maybe in these cohomology theories everything is free. There is a version, a smaller, very small version of the Brown-Peterson cohomology, which is Moravaki theory, which is basically taking one of the generators of the Bordism ring, one, and localized there. That's the Moravaki theory. And it was also shown that for the Moravaki theory, that if you go and take an abelian group and you calculate the Moravaki theory of this abelian group, again, it becomes a very nice free object, and these are here, again, the formal group laws, which you can think as they state. So that led, at the time, Hopkins and his crowd to ask the same question. Is it going to be always that whenever you have a complex-oriented cohomology theory, that the cohomology of the classifying space of groups is going to be free with respect to the ring? Well, it was supposed to be yes for some time, and then Igor Chris at the end of the 90s, or the beginning of the 90s, showed that there is a specific Silov group of this specific group on which just everything destroys by some non-trivial spectral sequence argument, and but somehow the question stopped there because of this counterexample. But let me then show you really quick why this is a question of non-commutativity. If we have a cohomology theory and we want to understand what is the cohomology of the classifying space of a group, but we divide by the order of the group, then it turns out that you can detect everything with the abelian subgroups. So if you don't care about torsion, then everything you can detect it with the abelian subgroups. So the whole point is that if you want to detect something that is non-commutativity, it has to be in the torsion part. So it's not a free part in some sense. So and at the time, Hopkins, Kohn, Ravenel, when they were talking about Moravaki theory, they calculated the rank of the Moravaki theory associated to a finite group, and they showed that this sort of commuting tuples of the group, and they gave a specific calculation of the rank of the KT rank, the C2 rank of this object, and they somehow expected, that's why they expected it to be free, and they gave some sort of groups on which this is the case. The groups on which the Morava KT of the classified space is a very nice free object is whenever you can detect or you can calculate the KTs of the bigger group through transgressing the classes from the smaller groups. If that's the case, then they call these groups good, and you could show that this object is concentrated in even dimensions. And they gave some list of groups on which this happens, and again, abelian, metacyclic, some direct products, some list that has some properties. Another list of groups that may have the property, but of course there is some non-trivial physical group of this group on which this does not happen. But again, it's a very incomplete list, and this is what is known. So, so again, the homotopical version of the question that I said at the beginning is also somehow not a free module by this calculation of Weaver-Christ. But let me just somehow tell you what is like a little story. Of course, if we know that if we going to calculate the equivariant K theory, the equivariant K theory is very nice, and it's a free module over the K theory for any group, because this is just representations. But if we take the geometrical version, there is a counterexample of that, and there's a torsion by the Bogomolov. If we take the homotopical version, there is something by the Silov group, by the Morava K theory. It's not known whether this counterexample in the geometrical sense will give one in the homotopical sense, and vice versa. So, since this is as much as we know, and the Bogomolov appear there, so of course one would like to understand how does the Bogomolov relate at all to this question in topology. So then I go to the world which I'm not very good at, which is algebraic geometry. So if any mistake is there, correct me and I'll try to tell you. So what is this unramified Brauer group? This is due to Saltman in the 80s, 90s. And the idea is to get a smaller subgroup of the Brauer group for any field, which because it's small and traceable, then might be easier to understand than the whole Brauer group. So the idea is to somehow to get the objects in the Brauer group which are unramified at any discrete valuation ring, and then he defined the Brauer group of the field that is unramified as the intersection of all these images, namely all these elements that are unramified at any discrete valuation ring. And what is good and nice, that was shown by Professor Pantev yesterday, is that we have this very nice isomorphism that if you have a smooth project, if you reducible variety, then the unramified Brauer group is the same as the Brauer group of the variety, which is the same as the Artin-Mumford invariant. So it is, in that sense, one can calculate it in this right-hand side. That is a very nice, very rational invariant because of this left-hand side. So it's a quite nice thing, these isomorphisms. Now, it was Professor Bogomolov who gave a more explicit calculation of what is this Brauer group whenever you have G acting on a faithful representation. And then he showed very smartly by understanding how this field of fractions, invariant field of fractions, is with respect to the abelian subgroups, that the kernel of all the restrictions to the abelian groups, so if you again imagine this is the non-commutative part of that. If you have some object there, well, you take all these kernels of all the restrictions. If you have any certain element of the Schur multiplier which restricts to zero in all abelian groups, then you get something interesting. And he showed that exactly that object that you see doesn't depend on the representation. It's nicely because it's a more stable invariant. It doesn't matter how many representations you add, the answer is the same. That the unramified Brauer group of this field of invariant fractions is exactly that. And of course, with that, he was able to construct several counterexamples of the rationality problem. And so this is another appearance. Of course, it was prettier than the one we showed. Shares the same principle, namely is something that is non-abelian. And of course, this is the homological version, and I was showing the homological version. And where does this also appear? So what I'm trying to show you is that the appearances of this gadget into several objects, and so maybe we can try to see how they relate. The other place we get up here is in the Ekedal invariance of the finite group, and this is from the Kontsevich construction of the Grothendieck ring of varieties. So namely, we're going to put all isomorphism classes of varieties, but then we're going to put this relation. We're going to split them into these. Namely, you have a closed set, and then we're going to simply separate the variety by the variety without the closed set and the closed set. And this, we impose this relation, it becomes a ring, and in this way, the affine lines and the projective space becomes and this equation. And you may think of it as that this is generated by smooth projective varieties, but whenever you see this, whenever you impose this relation, whenever you have a blow up over a sub-variety. Now, the Kontsevich multiple ring is the completion of that ring with respect to some penetration, localized at the inverse of this. But what I want to, and I suppose Enrique perhaps will talk more about it, because I'm not going to talk more, there was a construction of Ekedal to get invariance out of this object, so detection of homomorphism, and one of the ones he constructed was this detection of homomorphism, going all the way to the cohomology. So on the right-hand side, there is some formal sums of abelian groups with some variable to detect the dimension, and he put forward the definition of what would be BG in this Grothendieck of varieties, which would be this limit that is here when you have some faithful representation. And in this way, he could say, okay, BG is part of this Grothendieck group of varieties, and this map on there allows us to detect information.
Sorry, can you explain that?
Yes.
Okay. How do you arrive at this description of this?
What should I explain?
So what's the statement relating?
The statement is that, okay, we have varieties, but BG is not a variety. So we're going to call this BG. This is because it's some sort of the classifying space that you take this representation and then you just make it bigger and bigger and bigger and bigger, the homotopy type.
It's kind of a definition, sort of.
It's some sort of so it's all some sort of. So it's this gadget somehow, because you're at allowing the dimension of the representation to be bigger, somehow you're making the homotopy groups to be the right thing, in some sense, to match the ones in here.
What is N?
What is N is the dimension of the representation. I never said that. So that you want this whole dimension to be 0. So N matches the dimension. And the whole idea is, of course, you want to change these gadgets by a conjective smooth resolution, and then you want to calculate the cohomologies on this right-hand side. And so Ekedal, and in this beautiful paper, he basically defined. He said, well, I'm going to call some invariants of the group, the ones coming from that map that I said, which is you just take a resolution of that algebraic quotient, and then you just find the cohomology of that gadget appropriately with the appropriate dimension. But let me somehow give you the calculations he did, which I'm putting them all here. So the negative ones are 0. The E1 is 0 because it's rational, so no fundamental group. And the point is that the second one, he showed that it's the dual of the Bogomolov already. The second invariant of this BG was already, again, the same appearance of the Bogomolov, but the higher ones, well, he didn't do them, and they are not known so far. And of course, one could ask whether this is an obstruction for rationality, that these things are not 0. You may have that the Bogomolov is 0, but some higher are not 0. And also, this is my question to myself, is this related at all to the equivalent Bordism? So, you can imagine that the question in Bordism is very difficult, to me at least, because we were doing surfaces. Surfaces are not like real surfaces. Curves, smooth curves, which are not so complicated. But if you go to 3 dimensions, then it becomes very correct. And so then I was somehow trying to see how can I get some ideas about algebraic geometry to the topology, but let me just give you another list of groups on which the Ekedal invariants are 0. So these are different lists of groups on where the invariants vanish and whatnot. But one would like to have some sort of generalization of all these things, either by the equivalent Gordon groups, either by the unramified Barrow groups, either by the Ekedal invariants. And there is one somehow beautiful construction due to Colliot, Telen, and Ojanguren, which is the generalization of the unramified Barrow group to general dimension, which is using Galois homology. And the idea is somehow to extend the construction that is done on the Breuer group to all the higher homologies whenever you simply do the same type of idea. So namely, you take the intersection of all the kernels. This map here comes from a short exact sequence by the same type of idea. You take a discrete valuation ring whose field of fraction is k, and then you get this sort of, instead of, I could have put image like in the previous case, but this is a little nicer. You take the kernel of all these maps, and then you call this the unramified homology of this field, and where, of course, I never told you, but the homology of this field is defined as the homology of the absolute Galois group. And then in this way, they managed to propose a new set of invariants for rationality, because they showed, well, the second homology of your field when it's unramified is the same as the unramified Breuer group, but of course there are higher ones. If k is purely transcendental, that is 0, then it becomes a very nice set of obstructions for rationality. Problem is, it's difficult to compute, and so, but they are there. In the case of a finite group, this the 90s, Pei wanted to see what happens at the degree 3, third level. So this becomes not at all trivial, but he showed that the, say, this invariant one level up, some sort of higher model, whatever, this is the unramified group of this field of fractions, is some object that only depends again on the group. So now you can forget about the representation again. And it is cohomology classes that this person called it unramified, namely the cohomology classes of the group that when you somehow restrict and integrate along the fiber are 0 on all possible centralizers. This is related to localization formula. But then you need to divide by some classes that are called negligible classes. These are classes on which they don't give anything at the level of the Galois group. And then he showed that these negligible classes are exactly the ones generated by the second term classes of all possible representations. And with this beautiful calculation, of course, one can go and calculate for some group where this is not 0, and then you get another set of groups on which you could show that it's not rational because this is not 0. So, of course, if I want to put a 4 and a 5, I don't know that anybody knows. But this is some sort of another set of invariants that are, again, non-commutative by nature. As you might see here, this is the non-commutative part, and again, you kill this C2, which is some sort of commutative also, so you get some sort of the non-commutative part at the core of the non-commutative part. And so, this is, I'm just telling you what I haven't done, no? And there must be some sort of fantastic relation, but I don't know exactly how the fantastic relation is. So at the level of 2 dimensions, or not n equals 2, there is that the torsion of the equivalent unitary Bordism group is given by this homological version of the Bogomolov multiplier, which is equivalent to the Ekedal invariant of the group, which is equivalent to the unramified Brauer group. And one would expect that there must be some sort of relation that I haven't been completely able to tell you what it is because I don't have it, which is what are the 3-dimensional manifolds that do not bound equivalently, if you have a free action, and at the same time, what is the relation, which is this non-ramified group, and what would be this third decadal invariant. So this last part of this last slide is telling you all the things that I haven't done, but all the things that I've been trying to do, because there is some sort of relation to these things, but since I don't have a definite result, I cannot put it there. But the underlying question, which I don't know how to pose it, is that if we take the equivariant unitary Bordism ring, the free part is detected by the fixed point data, in as much as the symbols detect some sort of the fixed point data, as Kontsevich was showing. The torsion part is something that is not detected by this abelian part and is highly non-commutative, and then is torsion, and then it has to be detected by other means that is not fixed point data. And it's not that I know anything about atoms, but I suppose the atoms are there in this torsion part. What is curious that it appears in different disguises in this algebraic geometry setup, but as with many people we spoke about, it should be no surprise, because any manifold that you can imagine in all these cohomology theories is always algebraic. No matter what you do, all the manifolds that you can actually get, there is always an algebraic counterpart. So in these algebraic topology setups, even though you might think it's all differential, at the end you will find an algebraic counterpart. So having said that, it might be that the invariants here are going to be related to these invariants in algebraic geometry, but I don't know, and I think Enrique will say something about the secondary invariants from another perspective, but this is what I wanted to say. Thank you very much for listening.
Questions?
So I didn't quite understand what you mean by there's an algebraic counterpart. Can you?
Well, the word is in question is a question about manifolds.
Yes.
But if you go and look and you calculate topologically what are as an algebra, what are the subject, okay, and then you go and look at generators, you will always find algebraic generators. There is no single instance on which there is no algebraic generators on this unitary Bordism ring. Even in the oriented case, there is a professor in Hawaii, his last name is Doberman, has been showing that all possible things that is all algebraic. You can always find algebraic counterparts for all the manifolds. So underlying, even though it's a smooth thing and perturbation and intersection theory, in the differential setup, it's all algebraic. So having said that, is that, as I said, that even if I have some torsion objects at the manifold level, this is some sort of algebraic gadget that I haven't seen how to relate. In one in topological sense, some manifolds, but in some other sense, it's some transversal intersection with some section that I don't know exactly how to get it. But in that sense, is that it should not be a surprise that they're related, because there is this somehow idea that anything that you hook in Bordism will have an algebraic object that generates it. In that sense.
Is that the source, supposed to be the source of the relation between birational geometry and, I mean, in the previous slide you had these three things?
Yeah, so there's a should. So I don't know exactly how, and this is just, as you can see, this is just in dimension 2. One might think it's just out of luck that they happen to be all the same, or is that there is something that we are not seeing. But you know, I was thinking topology, you have the natural numbers are 2, 3, and infinity. No? After 3 is all similar. 3 is very difficult, and so we are stuck here at the level 3. So this is a 3-dimensional manifold with action, but there are this algebraic information that is here, as I showed it to you, because of this people Bayer did it. It's completely geometrical. It's just Chern classes. It's just so it might be that I would be able to say something here by knowing this answer. This is so my intuition is that the torsion part is this one, but I haven't been able to prove it. There is a lot of some more three-dimensional world which I need to get over. But I don't know the relation, and there must be something that I don't know how to get it.
So more or less, it's like you said that these generators, once fault, can be also taken as algebraic, right?
Exactly.
So you expected the existence of the counterexamples to this equivalent Bordizzi conjectures are related to some kind of like G non-rationality properties of these generators?
Yes, it's just I need to see how. Because some sort of, as you might see, this birationality problem somehow is living in the core or in the atom or whatever, and that part looks like some classifying space of some sort, so it's very related to the topological questions. So because it's a birational thing, it lives on the core, so you don't really care about what happens on the divisors. So somehow why in this construction by this thing is basically telling, well, get rid of whatever goes around on the divisor. Somehow that's not what we care. You care of the core, and the core is somehow very closely related to the classifying space.
Other questions? If not, let's thank Bernardo. Thank you. Tonight at 7:30 is the conference dinner, and it's going to take place in the restaurant, which name is Floor. And so the address is, I guess that's Народно собрание 4. This is I don't know if it's a street or that's a place, but that's the address. So it's just opposite to the building of the parliament. So it is the parliament, and it is a big statue erected in honor of Alexander II, who liberated Bulgaria from the Turks and Russia from themselves. But in any case, so he is called liberator, but it means different in different countries. And so he is the yeah, I mean, grateful Bulgarians erected this statue for him. The grateful Russians killed him a year later. But in any case, so he is the restaurant. He is the parliament. So he is the statue, and the restaurant is somewhere. All right, it's a great pleasure to introduce Alexander from Vienna, who is going to tell us about what he's going to tell.
I'm going to tell you about potential projective coinvariant algebra. Something about Zagreb as well. Thank you. So my talk only has, has some connections to the topics discussed here. At the end, I'll make some comments about directional geometry, and there are finite groups acting as well. But it's really a very classical talk with a slightly new spin on it. So before I introduce this thing called the projective coinvariant algebra, which has invariants are a slightly new thing, let me recall you the classical story. So there is something called the coinvariant algebra. So of course the word coinvariant is overused in mathematics, but there seems to be something that's called the coinvariant algebra. So here is the construction. So n is some positive integer, so it's often denoted Rn. So what you do is you take a polynomial ring over a field. and then divide by invariant polynomials under the symmetric group which have positive degree. So explicitly, because we have the theorem on symmetric functions, so this is modulo the elementary, so we take the polynomial ring and then we take the elementary symmetric polynomials. So this is a remarkable ring, so let me just list, so let's list some properties, so this is the following properties, so this is a K algebra, and it's finite dimensional, and its dimension is n factorial. It's graded, so this is graded by polynomial degree. Because we have a graded ring and these are graded generators. So instead of just this dimension, we can take its graded dimension, which I'm going to denote in Q, Rn. So the definition of this in Q is just that it's the sum R and K, the dimensions, then R and K, Q to the K, so it's the generating function of dimensions of graded pieces. And so that's the definition, but the statement is that this is actually the Q number factorial, where NQ, KQ is Q to the K minus 1 over Q minus 1, and then factorial is you multiply all of them together. So this is a graded algebra with some very specific combinatorially meaningful Q dimension. It's also, as a graded algebra, it has a cohomological interpretation. So Rn is isomorphic to the cohomology of the full flat variety, ELN mod P. So this is something called Borel's isomorphism. And the last thing that I want to say, which is perhaps the most interesting one, is that the symmetric group, of course, still acts on the co-invariant algebra, because we've taken an ideal of invariance. So as a K, so I guess, yeah, I think this is always true. So Rn is isomorphic to just a regular representation as an ungraded, that's just a vector space. But as a graded vector space, it has some interesting structure, and then you can take something called its Frobenius, Q-Frobenius character. So this basically means you just decompose. It's a mixture between this construction, but I'm going to now decompose this as a direct sum of representations, of irreducible representations. And the question is, what's the multiplicity? So of course we know the multiplicity here is just a dimension of each representation. But the question is, what is the Q multiplicity of each representation in this Rn? And then there is a very beautiful combinatorial formula for this. So this is, well, the characters of the symmetric group I parameterize by partitions of n. So this is going to be a sum over partitions of n. And then there's going to be, for each partition, there is the sure function or the irreducible representation corresponding to lambda. And then there is a combinatorial expression here. And there are going to be combinatorial expressions of other types later, and I don't want to spend too much time on this. But the answer here is you have to take some overall standard Young tableaus of shape lambda. So T is the standard Young tableau, and then you have to put some invariant of that Young tableau. So this is some kind of combinatorial sum, or it's sometimes called a fake degree or something like that. So this is some kind of nice combinatorial sum involving familiar objects involving standard Young tableaus. So this is a theorem of Stanley and Lustig. So this completely determines the representation format of representation content of this covariant algebra. So this thing crops up all the time. So this is several sections of Stanley's big book can somehow be brought to bear on this thing, and it sort of seems cropping up a lot of different mathematics. So the thing I'm interested in is looking at the following construction. So now, having set this up, we could take a decomposition of n. There's not a big difference between a partition and a decomposition, but that's more natural here. So a partition has parts which are ordered, and then a decomposition, it doesn't have to be ordered, but that does not make a big difference. So these are just positive integers summing to k with no order condition, but it doesn't really matter. Summing to n, sorry. So this is a decomposition, but if you want, you can replace it by partition. And then there is a standard Young subgroup S alpha, which is a subgroup of Sn. So this is a product of the S alpha i's embedded in the obvious way. So we're just permuting different parts of the tuple. And then then there's this algebra R alpha, which is just the invariant part of the convariant ring under that subgroup. So Sn still X, so you can look at this subgroup. And this is a similar list of properties. So this is a K algebra. Let me maybe put it together. So graded K algebra. The dimension is n choose alpha. So n choose alpha means this is the multinomial coefficient n alpha 1 alpha k. So this is n factorial divided by the product of the alpha I factorials. And q dimension, just the q binomial coefficient. So that's that statement. And the other statement, which will not be so important, but it's somehow interesting still, is that this R alpha is isomorphic to the homology of a partial Frege variety, GLN mod some parabolic corresponding to alpha. So that as a graded algebra, this also has a cohomological interpretation.
Sorry.
Yes.
It's a K algebra, but what's the Q dimension?
Sorry? The Q dimension is a graded K algebra. So the Q dimension is here.
Q is a grading.
Q is the dummy variable for my grading.
I could not see.
Yes.
From the camera.
Yeah. So so this is just a vector space dimension. It's a finite dimensional vector space as a graded algebra, and this graded dimension. So this is a Hilbert series.
Hilbert polynomial, yes.
Yeah. And yeah, that's right. And so in particular, an example of this would be the Grassmannian, where I take a decomposition consisting of two parts, k and n minus k, and then I would just get the Grassmannian here.
Otherwise, you get like a partial Frege variety.
And a partial Frege variety. Yeah. These are partial Frege varieties, exactly.
And this is quantum cohomology or regular singular cohomology?
Ordinary. I'm not going to do anything quantum. Q here is not. It's just regular singular cohomology graded. Yeah. And for that, I probably want k equals q or something, or k is subtle. Yeah. So yeah, let's take characteristic case. I have no idea about anything. Right. So let me just do a quick example of how this works, just to kind of remember, because that example will come back later. So when it equals 3, everything is kind of very, very explicit. That's the first interesting example. So here we have, so R3 is some three-dimensional algebra, x1, x2, x3, modulo the product, and then the sum. So that's a six-dimensional algebra, and so the q dimension is 3q factorial. So this is q plus 1, q squared plus q plus 1, and then inside here, really the only non-trivial r is r21, which is that thing under the sort of obvious S2 action, flipping x1 and x2, and so this is some three-dimensional algebra, and its thing q r21 is that thing divided by its 3 choose it's 3 choose 2 q, so this is just q squared plus p plus 1, and of course the corresponding partial factor here is just p2. So the GL 3 mod p21 is just isomorphic to the projective. Okay. And so this is the homology of the projective plane, this is the homology of the full 3-step flag variety.
Question.
Yeah.
Is there like a geometric view of what's Q? Like some Schubert simplification you have in the flag variety or something?
Yeah. So these things are these are all motivic. These are motivic decompositions. So there are actually all of these things are paved by affines, and you can think of this. Yeah. I mean, in different ways, of course. You have to. Yeah. Right. So I could write these are really L instead of cohomology, you could actually write motivic decomposition here. If you want. Yeah. Okay, so that's the classical story. And so let me now tell you the new take on this, which is a projective version, which will take us to more interesting geometry. So,
sorry, can you
yes.
just remind us of the definition of the P? Where's P?
It's a parabolic subgroup, so it's, I don't know, sorry, yeah, it's a parabolic subgroup.
Okay.
Yeah.
Thank you.
And there's only one
Yeah.
interesting one. Yeah, sorry. Okay, so what's a projective version? So one way to think about it, although this is not how we got to these results that I'm going to describe, one way to think about this is that what you're really doing here is you're meditating geometrically. You take sort of n copies of A1 and then you think of the Sn action. So that's the coordinate ring of n copies of A1, and then you kind of meditate over the symmetric group action on that space. So here is then the projective generalization, which is somewhat interesting. So we're going to meditate over n copies of P1. P1 cross P1, and then the symmetric group action, and see what you can squeeze out of sort of similar ideas. First there's a ring. So this is going to be P and tilde. And P and tilde is just a coordinate ring, so this has the Zager embedding into a large projective space. And I'm going to take, so maybe let's start with this one, so Zager embedding P1 cross P1, and if you look up your projective geometry 101 notes, then this will embed into P to the 2 to the n minus 1, so it's some large projective space. And I want to take the coordinate ring of that embedding, so I'm going to call Pn tilde, so that will play the role. I didn't give this a name, it's so simple, but here it's a bit more complicated. So this is going to be the thing in the numerator, so to speak, and that's just a coordinate ring of this embedding. Coordinate ring of P1 to the n inside P to the 2 to the n minus 1. So let me describe that ring. So that has a very explicit description, so let me just describe that ring. So this can be described, of course, very explicitly. So this P and tilde is a polynomial ring which has one variable for each subset of 1 up to n, including the empty one. So there's 2 to the n of them. So that's the embedding dimension, so that's how many variables we did want. And then you have to divide, so of course this is not a free ring, so we divide by, turns out that relations are in a very nice form. So xi xj equals xi intersection j xi unit j. So these relations are enough. So here r and j are subsets of 1 up to n, and then you have to impose these relations on the variables. So it's generated by a large bunch of quadratic relations. So that's the corner thing. I mean, that's basically the relations. That's still basically algebraic geometry 101. Okay, so where this gets a little interesting is the following. So of course this ring has a large Krull dimension because it corresponds to an embedding of this big fat projective variety, but this is like the main definition of this part of the talk. So let consider the following elements. So let ei tilde be the sum of these variables xi such that the number of elements in I is k here is k. So this thing is an extra grading, so that's maybe one message here. So of course this is a graded ring because this corresponds to projective variety, so it has one grading where every element here is graded degree 1. So that would be the standard projective grading. But it has a second grading, second interesting symmetric grading, which is exactly this one, which is I count how many elements there are in my subset. So that's a hidden new grading, which you don't always think about in projective geometry, but here it's very nice, and these are nice elements of fixed by degree. So yes.
That grading corresponds to what we had in Q.
I'll come to that. What corresponds? Now this is a separate story, and then I'll relate the two stories. So yeah, so there's an interesting twist there. Okay, and also give a bigrading to pi tilde by setting the bi degree of some variable xi to be 1 xi to be 1 comma I. That's what I should have written first. So that they put that there. And then we have these, so these are in bi degree 1k. And so here, 0 less than or equal to k, less than or equal to n. So I have n plus 1 such elements. And so here is then the sort of definition proposition theorem. Maybe I separate it into separate statements. So maybe a proposition is, so we discovered this with my collaborator Praise Adayemo, but this has been discovered a couple of times in different languages. This is not yet, a lot of what I'm going to say was discovered by different people in different languages, but this is not deep at all, is that these elements, E0 tilde, E1 tilde, and En tilde in Pn tilde form a regular sequence. And so that's very nice. So there are n plus 1 elements here forming a regular sequence. Notice that the dimension of this is the dimension of this variety plus 1. So this is the maximal regular sequence. This is the biggest regular sequence you could hope for. So now comes the definition. And this is the projective coinvariant algebra. Algebra is Pn. You take Pn tilde and divide by this regular sequence. So its definition is completely analogous to what was there before. That just disappeared. But it's a much more interesting algebra. So algebraically, before we had a complete intersection just in an affine space. Now we have this complete intersection in, ring theoretically in a very, very interesting space, which is this embedding. These are projective Gorenstein embeddings. So these are Gorenstein rings. These are graded Gorenstein rings, but they're not at all complete intersection. They are interesting Gorenstein rings. In fact, in Niles Reed's theory of building varieties from Gorenstein rings, a lot of these show up already. So some of these are, of course, extremely well-studied Gorenstein rings, but they have interesting structure.
So, what does regular sequence mean?
Okay, so it essentially means you're taking a complete intersection. So it's an algebraic notion. There is an algebraic definition which says that if I take successive quotients of this ring, then an element is not a zero divisor in the next one. So there's an algebraic definition. But geometrically, it means that every time I take a new equation, I cut down the dimension. So I started I mean, if you think affinely, then this is an affine m plus 1 dimensional variety. I've got it m plus 1 times, so this is a bunch of points. And so this is a coordinate ring of a bunch of points affinely. So as projective scheme, this is empty because I've got it too much. But there is still a nice ring there. So that's the one I want to study. So that ring is the ring that we are going to be studying. So that's the next, okay, so theorem. And I should say, this definition is also, we wrote it down, but then we found it in a combinatorics paper of Brown and Olsen, although they slightly misunderstand it, but they define it and they prove some nice things about it a couple of years ago. So, and then this theorem again has a sort of, we prove some part of it. Then there is a paper of Raiku, Sam Wayman, I'll say which that bit is, and also my some contribution here from my PhD student Fabian Lavikan. So he made the last computation I'm going to say, or he remade it. So here's a theorem. So this Pn is a bigraded finite dimensional Gorenstein K algebra of dimension and factorial. So once again, we get the same K dimension. So the dimension of the K dimension is the n factorial, and so now it's bigraded. So I can define a TQ dimension. So let me get this right. T stands for the projective grading, so that's the first grading, and Q for the second one. So I will have to, so this is AN TQ. I have to say what this is. This is some famous polynomial. So this is some polynomial where if I substitute T equals Q equals 1, I get to n factorial. And we can even describe this Frobenius, so TQ Frobenius character. And once again, unfortunately, the formula was just there, but it's going to have a very similar shape. So it's going to be a sum over partitions, and then there's going to be some combinatorial term, and then S lambda. And this combinatorial term, there's going to be a very similar expression coming, but it is still a sum over standard Young tableaus of lambda, T1 of the standard Young tableaus, and there's going to be a Q to the some invariance to the major. So once again, I'm not going to define, I don't want to spend time on the standard Young tableaus, but there is some kind of very explicit combinatorial expression of the Frobenius character, of the bigraded Frobenius character of this representation.
So Q
yes.
again corresponds to polynomial degree?
Sorry?
Q corresponds to polynomial degree.
So Q corresponds to this K. So the T is the one here. So the T is the one responsible just for the projective, just for this being a projective variety. This is the one that we would see as being a projective variety. And then this Q is this new one that you get. It's essentially a slicing. I'll say in a minute. It's actually a very geometric sense. It's a slicing. So you take, that's the second one. So that's how I've written it. So T is the first grading, Q is the second grading. Okay, so that's a theorem. It's not a theorem. I'm going to tell you what this thing is.
Sorry, could you write in bigger letters the exponent of lowercase t? I can't see.
I don't want to.
Ah, okay.
That was intentional, so that I don't have to define it. On purpose. Okay? Smudge of T and another smudge of T. Okay, that was all intentional. So these are some combinatorial things. It's going to be similar to what I'm about to define, but I don't want to bore you with too much algebraic combinatorics. So, but let me define though the ANTQ, which is I mean that's a Hilbert function. So this is a bigraded Hilbert function of this bigraded algebra. And what is this AN T cube? This I am going to define, so this is the sum over permutations. And then it's going to be very similar, but now I'm going to be honest. So this is Q to the major index of sigma, T to the descents of sigma. So I have to tell you what's major index and what's descent, and I'm going to do this by an example. So let's say sigma is 23514. Maybe let's make it more interesting. 21354. Okay, so to calculate descents, you need to find the places where this permutation has this line, in this one line rotation, number goes down. So here the number goes down here, and then it goes up, and then down again. So this permutation has descents, has two descents, and the major index of sigma is the sum of the positions. So this descent happened in the first position, this in the fourth position, so this is fine. So there's some kind of definition. In general, the number of descents, or the descent index is the number of I such that sigma of I plus 1 is bigger than sigma of, is less than sigma of I. And then the major index is the sum of those i's such that sigma of I plus 1 is less than sigma. So these are very standard definitions. They were introduced in at least by a person like Mahler in the late 19th century. So these have been around for a long time. And so this is a generating function you get as a bigraded Hilbert series. And then there is a. So why is this interesting? So let me write down the next result, which is an observation, but that's really the new observation, or that's a new observation, and I think it's very nice. This following theorem, I mean, it's still not deep. That's something I observed last year. Is that in fact there is a flat family of algebras. I don't know, A T over just the affine line, so AS over the affine line AS, such that AS at S equals 0 is the projective algebra, and AS equals 1, and in fact, at any non-zero value is isomorphic to the classical coinvariant algebra. So the picture you should have in mind is that there is some parameter, and at S equals 0, since the coinvariant algebra at any other value, there is there's the projective one, and then there's the classical one. And so what happens here is a C star action, and what happens here is that this new guy has an extra torus symmetry, has an extra grading, exactly because it's a C star fixed point. So there's actually a kind of geometric point of view where there's a whole family. In fact, you can soup it up to a two-dimensional family, but one is enough for us, where this is really a degeneration. So this degenerates to that one, and as it degenerates, it picks up this extra grading. So that's one comment.
And that really doesn't correspond to TQ.
Yes, and let me just say that. So under this degeneration, the thing that disappears is the T. So that's where the projective one disappears. So under this degeneration, so for Rn and then Pn, so this is bigraded. So here we have the An T cube. And then here we're going to have AN1 cube. So this degenerates there. So this, I have to substitute T equals 1. So I lose one of the gradings. And in fact, that's a very old theorem of McMahon, that if you just look at the distribution of major index, then that is the 2 factorial. So this is NQ factorial. So this is a very classical result in combinatorics. But there's another thing you can do, another specialization. So another specialization is Q equals 1. So in this specialization, you go from AN QT or TQ to AN T1. So this is where you only count descents. And this is the, here we set Q equals 1. So this is where we forget this extra grading, this what I think of as a combinatorial grading, and then we really retain the projective grading. And this is basically it just gives us the Hilbert function. So this is what's called a classical Eulerian polynomial. So the classical Eulerian polynomial, and that's known to be the, so if you compute the Hilbert function of just, so the dim, just the t dimension of this cover, which is the Hilbert series of this embedded variety, then that's just, that's equal to A and T modulo product 1 minus T to the m plus 1, well, I don't know, 1 minus T to the m plus 1. And this is a classical result. So this is in many books on toric geometry and studying the coordinate ring of the n times embedded P1. So this is not interesting. It's nice, but it's not certainly not new. This is also not new, but somehow combining these pieces together in this way appears not to have been done before, and you get this very nice kind of geometric picture of the degeneration, and everything sort of fits in very well. So that's the story just for the projective version. Let me extend it to these young subgroups and then do an example. So now, if we go back to taking this decomposition of N, and then we have the young subgroup inside the symmetric group, then of course we can also set, first we can set P alpha tilde to be Pn tilde S alpha, the invariant part, yes?
We've seen before this classical Rn was a cohomology of a complete flag variety.
Right.
And can we see Pn as a cohomology of similar like geometric representation?
Yeah, so that I don't know. That's a very good question. So this one also, yes. So the Eulerian polynomial is known to be the concurring polynomial of the permutohedron, so the permutohedral toric variety. So that also has a cohomological interpretation. But this, I would love to see, so this two-variable thing, I don't know a cohomological interpretation for. So it's, I mean, you could guess something from Horst theory, but then these varieties are very, very simple Horst structures, so that doesn't work. I don't know. So that's a good question to give a full cohomological interpretation to that bi-graded thing. I don't know the answer. So for this one and this one, it's well known and classical essentially, and there is some interpolation. So it turns out that the permutohedral toric variety, and between the full flag variety and the permutohedral toric variety, there's a whole family of things that are Hessenberg varieties, and so there's an interpolating family between them. But these are all just Poincare series of fixed varieties, which kind of moves from here to here. But this two-variable thing, I don't know.
And does this flag family comes from some geometric construction? Or?
This one?
Yeah.
It's something very silly. I can tell you afterwards. It's in a way, yes, there is a way to think about it a little bit geometrically. But to construct this family, you just put in, there's a way to put in, I wrote down the relations and I just put in somewhere. And I can tell you, one of the relations is x empty equals 0. Because remember I said that, so this is just E0 tilde. If you go through my definition, that sets one of the variables to 0, and you can replace it by x empty minus s equals 0. That's it. So it's some silly thing. But it works.
Thank you.
But you can think of it, yeah, I mean, we can talk about it. Well, there's a way to think of it a little more geometric. Okay, so what happens there? So you can take invariance there, or you can take invariance after you've taken that quotient. And so maybe I'll write here. So here are the statements about these guys. So here so the P alpha tilde is actually nothing but it's isomorphic to the coordinate ring of a general product of projective spaces. And then it has to be embedded in, I don't remember what the number here is, wherever this wants to be embedded, and that works out all very nicely. So in fact, these projected versions of these partial coinvariant rings is nothing but, the covers are nothing but Zagra embeddings. So this is a coordinate rings of Zagra embeddings. I think that's quite nice. I've certainly not seen it before. So this organizes all the coordinate rings of the Zagra embeddings into this kind of nested structure, very just controlled by invariant theory.
So a question.
Yes.
I keep asking things.
Yes.
Because, what do you mean by coordinate ring of embedding? Is it of the image or?
Yeah. Yeah. So this is algebraic geometry 101. So if I have a variety embedded in projective space, a projective variety, then this is the vanishing locus of some ideal, and by definition, the projective coordinate ring is whatever the coordinate ring of this is. So kx0 to xn modulo the ideal. That's a one.
Okay.
But
I mean,
no, you sort of want to include for affine varieties the coordinate ring is an invariant thing. For projective varieties, the coordinate ring depends on the embedding.
Yeah, I could see.
And sorry.
Well, basically it's intrinsic. I mean, you choose a line.
Yeah, sure, of course.
Yeah, so it's just.
Of course. And this is like, there's a standard one, the 111.
Standard one.
Yeah.
So you don't really need anything. I mean, you can give the line.
Bit pedantic, yeah, exactly. I could, the same amount of writing, I could put, yeah, but in the same random, embedded by 011. Yeah. Right. So the second statement is that this other one, so the P alpha is finite dimensional. And in fact, the dimension, the k dimension of the alpha is no surprise, it's n choose alpha. What is more interesting is the qt dimension, tq of p alpha. Okay, I'm going to once again just write a alpha qt, and then I have to define this a alpha qt. So that again is completely controlled by combinatorics. So these are going to be, I think, the last combinatorial definitions. So here, A alpha qt is the sum reverts in W alpha, the same definition. So T q to the major of W, T to the descent of W. Okay, so this is a definition, but it still needs a definition. So here, where W alpha is the set of words in multiset 1, 1, 2, 2, and so on. I'll give an example in a second where I take A1 of 1s, A2 of 2s, and so on. And so words should be clear what it means. It's the same as permutation. I have to list all my elements in that multiset in some order. And of course, 1s are indistinguishable, and 2s are indistinguishable, and so on. And for W in W alpha, there is an obvious definition of major W and descents of W. Once again, it will be obvious from the example. But you keep going up, and as soon as you see a jump down, you score a descent, and you remember where you scored that descent. So these are really the main statements, and so that this, together with that definition, is really the main result here. So this gives a complete determination of, in algebraic combinatorial terms, of coordinate rings of Zagra embeddings, and bigraded in this sort of very, I think, interesting way. So again, the singly graded version, so the T version is in the literature somewhere, but it's very much hidden. But this bigrading is new, and I think it's interesting. So there is, of course, no symmetric group action here anymore because we destroyed that in that Young subgroup. So there's no further statement. So let me instead do a quick example where how everything works here. So we continue the n equals 3 example. And so I have sort of two things here. I have the P3, and then I have this P21. And just for completeness, I'm going to put here P111. Sorry. Yeah, P3. That's going to be boring. So if you repeat everything, you can repeat everything for the multiset, for the decomposition. So this is really the language I've been using. This is P111. So this corresponds to the decomposition of K into 1 plus 1 plus 1, and then there is kind of the opposite one. So let's do the quick calculation. And I should say, I didn't say that, but the degeneration also works. Maybe I should have put here a third statement, sorry, is that under this degeneration, this P alpha is a degeneration of the R alpha. So that's fully compatible. So all of these things go nicely along the right. Okay, so what is this? So first I have to do the A3QT. So for A3QT I need 132, 213, 231, 312, 321, and circle the descent, so there's none here. This one, this one, this one, this one, this one, and this one. And so you follow the definition, so this is 1 plus, there's a QT here and a QT here, so it's 2QT plus 2Q squared T plus Q cubed T squared. That's the last guy. So that comes here. So the Hilbert series here is 1 plus 2QT plus 2Q squared T plus Q cubed T squared. And so what we have seen before is that specializing at T equals 1, and that becomes 1 plus Q times 1 plus Q plus Q squared. This is the one that we've seen before. And then it also specializes at Q equals 1 to 1 plus 4T plus T squared. And that's the Hilbert numerator. That's the numerator of the Hilbert function for P1 plus P1 plus P1 in P3. So that's of course an elementary exercise to calculate, but it's all in there. So for this one, I have to calculate A21 QT. So here I'm going to work with the multiset 1, 1, 2, and there's only 3 words that I can write down. 1, 1, 2, 1, 2, 1, 2, 1, 1. And once again, we can look at the descents. There's just 1 here and 1 here. So the corresponding polynomial is 1 plus QT plus Q squared Q. And that's actually interesting. So because of the Gorenstein symmetry, these are going to be fully palindromic. So and that's easy to see in the combinatorics also, that there is a full Poincare duality of the ring, which corresponds to a full palindromicity of these bigraded things. But that breaks here. And that breaks here because as graded rings, or bigraded rings, these are no longer Gorenstein. There is still a little bit of Gorenstein that's left because of the cohomological interpretation, but but these are no longer fully symmetric. So that's what comes here: 1 plus QT plus Q squared T, and that again specializes. So at T equals 1, this is the one we have seen. This is just a cohomology of P2, 1 plus Q squared, and then this other one at Q equals 1, which is 1 plus 2T. And this is again corresponding the denominator of the Sager embedding of P1 plus P2 in wherever this wants to be, P5. And then just for completeness, the last one is just 1. There's only one word in the multiset 1, 1, 1, so that's not very interesting. So you get this sort of embedded structure where the ring corresponding to this is embedded nicely in the ring corresponding to this. And everything is fully compatible.
So question?
Yeah.
So it's not written. So this P alpha is also defined as a quotient of P alpha twiddle with this
Well, either, or you can take invariants. I think I defined it over there as invariants, but both work actually. You can either define it as a quotient of this, or you can define it as the invariant part of Pn under the Young action. It's the same. Yeah, that was the definition I gave over there. But actually, you're right. This is also a quotient of VIHREN. I just quotient by the same ideal, because those ideals are in every one of these rings. Yeah. And of course, for alpha trivial, this is just the coordinate ring of Pn itself, and then I cut it down to 0 dimensions by taking away all the variables. So as a one-dimensional K-vector space. So that's the one. Okay, so right, so these are sort of the main results so far. But this is a kind of strange project. It develops in different ways. There was one very interesting direction. Maybe I have 2 minutes to mention that. So one dead direction in the project is the following. So there is a very exciting definition here, which is much more exciting and interesting than anything I've told you, is the double diagonal coinvariant algebra of Heyman. So Heyman's diagonal coinvariant algebra is you take 2 sets of variables, y1 yn, and then you consider the simultaneous Sn action, or diagonal Sn action. So where you permute the S's and the Y's together, so then you meditate effectively over A2 cross A2 cross A2, and then it's the same definition. You divide it by positive degree invariant polynomials. So this is Heyman's celebrated diagonal coinvariant algebra, which is some absolutely beautiful properties, which I'm not going to say, but in particular, this is also bigraded. So this is another bigraded SN module of finite dimension m plus 1 to the m minus 1, so that's some extremely famous, another famous combinatorial number. So that's Reed Heyman. So you can ask about its bigraded character, and this is relevant. All conjectures happen, and lots of stuff happening here. And so here is a proposition which unfortunately isn't very exciting. So proposition, there is a natural ring homomorphism. This is very easy to write down. From my thing to his thing. Now this is not very surprising because I have P1 cross P1 cross P1 and he has A2 cross A2 cross A2, so that's really compatible. Now, which however factors through the maximum ideal. So it dies. But it's a non-trivial, it dies for a very non-trivial reason. So the fact, so I found this computationally, that my homomorphism was always on a computer, it was always giving me zeros, and the fact that it factors follows from a very recent theorem of Carlson and Oblomkov. So Carlson and Oblomkov have made some very deep study of the module structure of this diagonal coinvariant algebra, and in particular they have a result which has a very non-trivial consequence that this homomorphism actually is trivial. But it's a bit disappointing. I was hoping to find some nice submodule maybe of this DN or something, but it wasn't to be. It's trivial, but it's trivial for a non-trivial reason. So that's kind of non-trivially trivial homomorphism. So that's also interesting. So where else can one go with this?
Sorry, what was the size of this thing?
Which one?
Of the left-hand side. No.
That was n factorial.
No, the one below.
1. So it's size. 1. It's a one-dimensional K-vector space. It factors through the positive degree. It kills everything.
I would just P plus.
It kills everything, yes. Unfortunately. Or I don't know, yeah, plus.
Okay.
So So it kills the unique maximal ideal, and if we are left with, yeah. So it's a trivial homomorphism. So if you write down these generators, there's a natural way to map these xi's to here, and then you see the images, and they're all zero. And it's a non-trivial zero. It's zero. So that's
you have
also
some geometric thing with the Hilbert scheme of this.
That's what, yeah. So the Hilbert schemes are obviously here somewhere, and yes and no. And this is a very algebraic. So this Gaussian-Oblomkov argument is somehow extremely algebraic. They understand module structures. Of course, it's geometric, and it has F-Springer fibers, and the paper is long and it has lots of geometry in it. But ultimately, this is an algebraic statement. So, but yes, Hilbert schemes are are here quite a lot. But I can't make an interesting statement at the moment about Hilbert schemes. But yeah. But that's really great. I mean, that's why I got to think about these things. But somehow there is no more geometry yet than I can tell you. Okay, so what else can one do? I mean, one interesting direction is which my student is computing now. I mean, you can look at the compositions which are sort of k to the m. So some guy repeated m times, and then so the corresponding ring P alpha is quite large, but it's still going to have an SM action. So this is some finite dimensional ring with some bi-graded ring with some action of some symmetric group, and then you can go away and compute characters. So you can compute this Frobenius T cube of this P alpha, and this is going to be in somewhere in the character ring of what's the character ring of SM, and we get some interesting combinatorial formulas, and they are not that interesting, so I won't bore you with them. But there's some nice computations that you can do for these kind of bigger things. Now, another direction where I've been doing some computations, and it seems quite interesting but intriguing is, and that's the last thing I'm going to say. So really, you can think of this. If you want, you can think of this as a subject in polytope theory. So P1 cross P1 cross P1. Torically, with this O1, so I don't know, it's a Oblomkov body or whatever it's called, corresponds to just the D cube.
We need to give us a line bond.
Yes. I always consider one-on-one. Yeah, absolutely. So I always want the Zig remedy. Yes, of course. Thank you. I mean, otherwise it would just stretch it, and that's also interesting. But I'm not, for now, I'm not going to stretch it. Now, if you just think of the D cubed, D cube in Z to the D, the standard D cube. Then basically what I've been doing is I've been doing Ehrhart theory. So when you take multiples of this, you take number of sections, then you're just dilating your polytope, and then you count lattice points. So there is Ehrhart theory, and then you can get to this AN T over 1 minus T to the n plus 1 from, I mean, this is the standard Ehrhart function of the hypercube. And so now you can, instead of taking the hypercube, you can also look at the following polytope, which is my generalization, some sort of C D L. This is all those numbers, 0 less than or equal to SI less than or equal to 1, and the sum of the XI is less than or equal to L, or some value L. So this is like a chopped hypercube. So for example, I could chop the hypercube here. And so my polytope could just be, so this is 3, 2 would be this chopped hypercube. Or I could chop it at level 1, which is just a simplex. And you can think about the Ehrhart theory, and everything goes, a lot of the things go through, rather. So if you take, there's a natural projective embedding here, and you can look at, and this still has the action of the symmetric group as D. So you get very interesting bi-graded SD representations. Now the infinite dimensionals are all there, and they seem to be interesting. You no longer have enough elements in a regular sequence, so you cannot now chop this down to a finite dimensional thing, which itself looks quite interesting. So you get basically out of this, you get some interesting class of bi-graded infinite dimensional SD modules, which have some interesting, nice combinatorial structures in them. So this is where we are thinking about. And in this language, just one final word about where this D comes from. So in this theory, this really is the counting for the dilations. So dilations really just a number of sections on P1 to the n, and then of whatever, k. So this is the projective one, and then where does this Q come from? In this language, the Q just comes from slice. So you're going to slice this picture geometrically, and that's really was our starting point. So the new bigrading really comes from this kind of symmetric slicing. So we're rotating everything around the main diagonal. So orthogonal to that, we have this slicing, and that's really the origin, the geometric origin of this bigrading is in polytope theory. And then it was natural to consider these chop guys, and then we seem to get these interesting bigraded SD modules that we are sort of thinking about at the moment. Thank you.
More questions?
Are all of these still Gorenstein?
Sorry?
Are they all still Gorenstein, the DNs and the PNs?
No, so these ones, no. Some are. There's one other Gorenstein polytope for, most of them are not. That's a good question. But there's one in the middle. That's also quite nice. So there's one in the middle for odd D, there's one in the middle, that's still Gorenstein. The other ones are not. And I should say, sorry, I didn't say that, I'll say something about projective birational geometry. I mean, in terms of birational geometry, these guys are between Pn, these are all birational models of between Pn and P1 plus P1. So as you move up the L, you're going to have flops moving from projective space Pn, and then you move a bunch of flops at a time to P1 plus P1. So the projective varieties corresponding to these are birational transformations between Pn and P1 plus P1, so that's interesting. And then there's one guy in the middle that's going to be final for odd D, but most of them are not going to be. Well, I don't know why they're final, but the class you're embedding them with is not some multiple of the canonicals. So the rings you're getting are not Gorenstein. And you can see that you already. Yeah, there's some interesting story about just this denominator, and already that's not symmetric anymore most of the time. But there's a middle one that is symmetric, and everything here is already also controlled by combinatorics.
Other questions? Yes.
So there's, I'm still a bit confused by one thing, which is the covariant algebra. So the standard covariant algebras, you can interpret it as you have your affine space AN, you have the SN action on it, and then you take the quotient, and then the covariant algebra is the coordinate ring of the scheme theoretic fiber over the origin, right? Right. And the same is true for this DN. It's just that you take the SN action on copies of A2. So is there a similar picture or a similar interpretation for this projective covariant algebra? Like,
maybe not so directly, because it's really, I mean, as a projective, it's an empty projective space. I mean, I've cut it down to 0 dimensions. The proj of it is empty, right? So it's a slightly different. I mean, invariant theoretically is the same construction. There's my trivial invariant, and I quotient that by all the other invariants, and that. But geometrically, I'm not sure. You tell me. But I think, I mean, not such a straightforward one, because projectively we're talking about the empty space. So. This is in the irrelevant idea if I think in terms of projective geometry. So, short answer is no, but there may be a better answer. But I mean, for us, it was really an invariant theoretic, a naturally invariant theoretic definition.
All right, let's thank Bausch again. So 3 minutes break, and then we continue with the talk and reading.
a place called a door. So it's the address is Narodno Sobranie. All right, so it's an immense pleasure to introduce Enrique Becerra from Miami and senior staff who will tell us a little bit about the field of mechanical performance. Enrique? Thank you. So it's about the
Sí, ya con eso ya. Ahí arriba hay
Okay, so thank you for the invitation. I'm very glad to have the opportunity to speak here. And well, I would like to talk about some preliminary ideas that we are working on, which arose from some current project in collaboration with Professor Ernesto and Professor Ludmil. So this is going to be very related with Professor Bernardo's talk. So in fact, we are trying to think of some very similar question as him. Well, this will give me the opportunity to elaborate a little bit more in this notion of ethical invariant, which appeared in this previous talk. So, well, in order to set the context, let me go back and review some history about this, or the introduction of this notion of ethical invariance. So, the story begins in 1917 with this classical question posed by Emmy Noether, which reads as follows and is connected with the inverse problem of Galois theory. So the question is, suppose that you have some group or some subgroup of permutations in some letters. We have here n letters, x1 up to xn, and we take some subgroup of permutations of that variables. So, so she asks whether if you take the field of rational functions in these variables, so you can also consider the subfield of invariant functions with the corresponding permutation action of G, and this will produce some field of invariant functions. And the question is, when is this subfield purely transcendental extension? So Geometrically, this amounts to ask whether the quotient variety that you can obtain by taking the quotient of the affine space of the corresponding dimension divided by the action of this group is a rational variety. Okay, so apparently at that time, it was assumed or it was believed that this question has an affirmative answer, that is that these varieties are all rational, but in fact, later on in the second half of the 20th century, there start to appear some counterexamples to these Nether's questions. Okay, so for instance, the first examples of such quotient varieties which are not rational appear in the work of Swan, and he proved that in fact, if you consider some cyclic group of prime order like that, and the corresponding quotient variety given by this cyclic action on an affine space, then for these three prime numbers there, then in fact and if you consider the base field as the rational numbers, then this quotient is not rational indeed. Well, these are some the first classical counterexample of the Nether's problem, and there are also some examples that was provided by Saltman using some cohomological obstruction that was introduced by Artin and Mumford in order to study rationality equations, which is what is often called the Artin-Mumford invariant, and which is related or is in fact given by the unramified parallel group of the field of invariant functions of this G action on a affine space. Okay. So in fact, what he proved is that if you take some field which are whose characteristic is not P for some prime number P, then in fact there exist finite groups of whose order are given by some power of this characteristic in such a way that the Nether's problem has a negative answer. Okay, so let me just recall some very basic definitions about what a Brauer group is. So suppose that you have some field K, this is capital K. So you can define the Brauer group of such a field as the set of isomorphism classes of central division algebras over K. And in fact, you can endow this set of isomorphism classes with a product structure, with a product operation in such a way that this becomes an abelian group. And in fact, this abelian group structure can be identified with some Galois cohomology group, which in this case is given by the second Galois cohomology of the absolute Galois group of K with respect to the with coefficients in the group of units of the multiplicative group of units of K. So in fact, in particular, if you take this capital K as a field of rational functions on some variety defined over K, then the unramified Brauer group, which appears in Professor Bernardo's talk, can be defined as a certain group of this Brauer group. Okay, so in fact, this construction, this classical construction of the Brauer group for a field can also be, well, it was generalized by the work of Asumaya, Aufelder, and Goldman in order to define a corresponding notion not just for a field, but in fact for any commutative ring. And this can be done using the notion of Asumaya. But in fact, these constructions, for the case of rings, was later generalized by Grothendieck in such a way that you can define the Brauer group in a much wider setting. So you can define the Brauer group scheme, stack, topos, or whatever. Okay, so let me just recall how the construction of the Brauer group of the scheme is like, how this is done. So suppose that you start with some scheme X, and you will define, you can define an Asumaya, by definition, an Asumaya algebra of rank n over this scheme is given by some sheaf of algebras over the structure sheaf of X in such a way that locally in the Adel topology it looks like a matrix algebra with entries in the structure sheaf. Okay, so moreover, you can also define the notion of Morita equivalence between Asumaya algebras. So two Asumaya algebras A and B will be called Morita equivalent whenever you can find some locally free sheaves of finite rank E and F in such a way that when you tensor this A and B with the endomorphism algebra of the corresponding bundles, then these two become isomorphic. Okay, so with this notion of Morita equivalence, you can take the set of Morita equivalent classes of Asumaya algebras defined in this way over X, and this by definition is the Grothendieck Brauer group of the scheme. So the product operation in this Brauer group is given just by the tensor product of Asumaya algebras. And in fact, you can prove that the inverse, for instance, this is in fact a group with this operation, and the inverse of an algebra is given just by the class of the opposite algebra. So if you start, for instance, with some vector bundle over X, then you can take the endomorphism algebra of this bundle, and this will produce an Asumaya algebra, of course. Well, this Asumaya algebra has a trivial class in the Brauer group. So these are the trivial elements in.
Sorry, can I ask something? We're working over a field and it's characteristic 0, algebraically closed. What assumptions are we making?
No, here is for an arbitrary scheme.
Okay.
So you can proceed in this general context, starting with some scheme, and this turns out to generalize classical construction of the Brauer group over a field.
Thank you.
Okay, so in fact there is also a cohomological interpretation. So the classical Brauer group of a field has a cohomological interpretation in terms of the Galois cohomology of the absolute Galois group of that field, and some similar, something similar happens in general for a scheme. And so in fact you can take, or you can consider for any fixed rank n the class or the set of isomorphism classes of Asumaya algebras over X, and this turns out to be identified with the non-abelian cohomology group H1 with coefficients in this non-abelian group PGL n, and this is just because automorphisms of Asumaya algebras are given by conjugation up to scalar multiplication, and this allows you to identify the set of isomorphism classes of some for some fixed rank Asumaya algebras with this group. So moreover, let's assume here that we are in the complex case. So we are suppose that we are working over the complex numbers from now on. And so you can consider the following short exact sequence, which realize the group of automorphisms of Asumaya algebras in this way. So this will produce some connecting isomorphisms, which take some Asumaya algebra into a class in this cohomology group. And in this way you obtain a map which goes from the Brauer group defined in terms of Asumaya algebras into this cohomology group of X with coefficients in the sheaf of non-zero functions over X. Okay, so moreover, if you consider as well the exponential exact sequence, then you can produce again by a connecting morphism some map which goes from here to the third cohomology group of X with coefficients with integer coefficients. And in fact, it turns out that any element in the Bragg group is a torsion element, and so this will produce some torsion class in H string. And this, moreover, turns out to be an injection. So in fact, you can realize the Bragg group of a scheme defined over, say, the complex numbers as a subgroup of the torsion part of the third homology group of X. But in fact, this is not always. So in some cases, in some good cases, this is in fact an isomorphism, but in general, you can have. So this is sometimes called the cohomological Bragg group, and in general, these two are different. Okay. So now back to the story of Ekedal's invariance. In 1987, then Bogomolov provided, in fact, an interpretation of the Artin-Mumford invariant within the context of Nether's problem in purely group theoretical terms. So recall that as in the talk of Professor Bernardo, the Bogomolov multiplier of a finite group can be defined this way, taking so the intersection of these pieces, which correspond to the abelian subgroups of J, and these will produce the Bogomolov multiplier of this G. So in fact, Bogomolov proves that this group can be identified, in fact, with the unramified Bragg group of the quotient variety, where here B is some finite dimensional representation of G which is faithful. So you can take such a representation, finite dimensional and faithful, and you can produce the quotient variety like this. And then the unramified Bragg group, which is a subgroup of the Bragg group of this quotient variety, is in fact isomorphic to this Bogomolov multiplier, which is defined just in this algebraic manner. So, in particular, this implies that, for instance, if the quotient variety is rational, then this group vanishes, and then the Bogomolov multiplier must also be 0. Okay. So now I will introduce this notion of Ekedal invariant, which generalize in some sense the Bogomolov multiplier, as I will explain later on. But let me first say some words about the multiplic value ring in order to be able to define the notion of Ekedal invariant. So you can start with some algebraically closed field of characteristic 0, and you can consider the category of varieties, algebraic varieties defined over this field K. Then you can take the set of isomorphism classes of these varieties, and this will produce, you can take the free abelian group generated by isomorphism classes of K varieties, and then you can take the quotient of this group by imposing these kind of relations. The first one is sometimes called the scissor relation, which allows you to take off some closed piece of X, and then you can split the class of X as a sum of these two subpieces. And you can also impose a relation given by the Cartesian product like that. So in this way, the corresponding quotient group becomes in fact a ring. So this K naught of bar is a ring. And okay, so moreover, you can also take the inverse of this particular element in this group of varieties, which is given by the class of the affine line. That is sometimes called the Lefschetz multiple in this ring. And then if you formally invert this element, then you will obtain something which is called the multiplic ring of varieties over K. Okay, so moreover, there is also some filtration of this ring, which is given in terms of the dimensions of the varieties which generate this ring. So you can define a filtration like this in such a way that with respect, you can complete take the completion of this motivic ring with respect to this dimensional filtration. So by doing that completion, you can start considering some limits in this motivic ring. Okay, so on the other hand, the very same construction can be done also in the context of a stack. So let me consider here this will produce the corresponding Grothendieck ring of stacks. So here stacks refers to the category of algebraic stacks of finite type over K in such a way that the automorphism groups of these for each point of these stacks are supposed to be affine. So this is a restricted class of algebraic stacks. And for this category of the stacks, you can just perform the same construction. So you can take isomorphism classes of stacks, and you can take the free abelian group generated by that, and then you can impose these two, the scissor relation and this product multiplicative relation. But moreover, you also need to impose an extra condition in this case, which says that, well, whenever you have some vector bundle of rank n defined over some stack, then the class of the total space of that bundle in this ring will be forced to be equal to the base times the class of the fiber. Okay, so this third condition in the case of varieties follows from the first two conditions, but for stacks you need to impose this extra condition. So this does not follow from the first two in this case. Okay, so at the end you will obtain some ring, like the ring of varieties, like that. But in fact, you can prove that there is some relation between the Grothendieck ring of stacks, defined like that, and the Grothendieck ring of varieties over K. So the point is that you can explicitly compute the class of the general linear group considered as a variety defined over K, and it turns out that if you can split the class of the general linear group in this form. So this can be written down in terms of as a polynomial of that form in the Lefschetz motive. So this is done by an explicit computation. And the point is that, well, you know that the class of the general linear group splits like this, has this polynomial form into Lefschetz motive, but moreover, you have also the corresponding classifying stack of this GLM. So you can consider the class of the classifying stack in the Grothendieck ring of the stacks. And since this VGLM has a universal GLM bundle in such a way that the total space of that bundle is just a point, so the class of the point corresponds to the unit element in the ring of the stacks, in the Grothendieck ring of the stacks. And so in this case, for this particular group GLM, it turns out that whenever you have a GLM torsor, then the class of the total space of that torsor is equal to the class of the fiber, which is GLM, times the class of the base, which in this case is the class of the classifying stack. And so this means that the inverse of the class of VGLM equals the inverse of this polynomial. Okay, so in particular, this implies that.
Excuse me, but could you explain one more time why we need this condition for this stack?
Why do you need this?
Yeah, what I mean, if we impose on those two conditions, if we impose these three conditions, what explicitly change on this?
Well, for varieties, whenever you have some trivial separation with respect to statistic topology, then the class of the total space of such fiber space splits as the product of the class of the fiber times the class of the base. So in particular for vector bundles, this is true if you impose these two conditions, just these two conditions in the case of varieties. But for stacks, this is not longer true that these two implies the third one. And in fact, if you think about it, you are losing very much information in this when you take this this splitting, because vector bundles over stacks also has this part which corresponds with representations of the automorphism groups of points. So if you split the class of the total space like this, then you are losing all this information of the representations of for the automorphism groups of points.
So I mean, this condition is to use this stabilizer action.
Stabilize the action.
Stabilizer.
In particular, this condition implies this one, and this allows you to compare this with the Grothendieck ring of varieties in a simple way. But this will not be true if you keep track of all the information given by the action of the stabilizer groups on the fibers of a vector bundle. You need to use all this information in order to being able to compare these two things like that.
Thank you.
Okay, so now using this fact, you can prove the following. So Ekedals show that in fact the Grothendieck ring of stacks can be obtained from the Grothendieck ring of varieties by formally inverting the Lefschetz motive and also all these polynomials in the Lefschetz motive. So this ring, we the class of the Lefschetz motive is already inverted. But if you invert all of these polynomial expressions, sorry, I think this must be something like L to the m. Yeah, so you need to consider all these powers like that. So you need to invert all of these polynomials. So if you invert all of these polynomials, then what you get is exactly the Grothendieck ring of stacks, like that. So in fact, once you invert all of these things, then in fact the Grothendieck ring of stacks can be compared with the motivic ring, with the completed or the motivic value ring, where you take the completion with respect to the dimensional filtration. And this is because once you complete the motivic ring, then all these inverses of L to the n minus 1 can be written down as a geometric series. So this makes sense in the completed motivic ring, and so you can produce some map which goes from the Grothendieck ring of stacks onto this motivic value ring. Okay. So now you can define the Ekedal invariant of a finite group in the following manner. So in 2009, Ekedal introduced this geometric invariant for finite groups. And the idea is that, well, you can start with some finite group G, and then you can consider the classifying stack of that group. So the class of BG will belongs to this Grothendieck ring of stacks. But since you have this map which goes from the Grothendieck ring of stacks onto the motivic value ring, so you can push this class of BG into this ring and try to understand how this looks like inside the motivic value ring. So this is by definition the Ekedal invariant of G, is the class of BG viewed as an element in the motivic value ring. And in fact, Ekedals compute explicitly how this class looks like in terms of these quotient varieties. So you can start with some.
Can I ask a question about Ekedal's theorem?
Yep.
Is there a version of it for just Billy Mumford stacks rather than all stacks?
I don't know. We are trying to think in that kind of problems.
Okay.
What kind of elements you need to invert in some way to obtain just the restricted ring of the Mumford stacks, but I don't know. It seems that you also need to consider fractional exponents of Lefschetz motive in some way.
So it seems harder, basically.
Yeah, it's harder.
Thank
you. Yeah. So so you can write explicitly the class of BG like this. So again, you can start with some finite dimensional representation of G, which is faithful, and in this in these terms, you can also consider this the Cartesian product of this B m times. So you take the m times product of this B, and you endow this with the corresponding diagonal action, and you can take the quotient, the corresponding quotient variety. So after this normalization, so this is the rank of the representation, and this m is just this integer index which is varying. So you can produce some element in the motivic value ring by taking the limit. So you can prove that this is in fact a convergent sequence in this completed ring. And in fact, this turns out to be equal to the Ekedal's invariant. And the proof is kind of straightforward. So you can just compare how so you can also consider the class the quotient stack of this action, this G action Bm, B to the m. So this will produce some stack, and then you can take the class of this stack to the motivic value ring by this map, this Ekedal's map. And then you can compare this and the class of the corresponding quotient variety. And if you do that and you take some suitable splitting of these things with respect to some subvarieties, then you can in fact prove that these two agree in the limit after taking this normalization. Okay, so these two things coincide, and you can in principle compute the Ekedal invariant using this kind of limit, but moreover you can also consider some invariants, some homological invariants which are derived out of this Ekedal invariant. So let me denote by L naught of the category of finitely generated abelian groups as a set of isomorphism classes of finitely generated abelian groups subject to the single additive relation, with just this additive relation. So you take the direct sum of two such groups, then the class of the direct sum equals the sum of the classes, like that. Okay, so you can take some integer. So for each integer n, which can be positive or negative, you can produce some map which goes from the completed motivic ring into this L naught. And in fact, you can define this just by taking homology and taking into account that you are inverting this L, and you need to shift the homology like that, taking into account this kind of normalization. Okay, so in fact, it turns out that this map HM is in some way, well, it is continuous in a suitable defined way if you consider the topology of this completed motivic value ring. And well, you can use these maps in order to produce out of the Ekedal's invariant some homological invariants just by taking the corresponding homology groups of this EG, which lives in the motivic value ring. Okay. Now, in this setting, what Ekedal's proof is that if you can compute the first the Ekedal invariance for these lower values of the index. So in fact, all the Ekedal invariants vanish if the index is negative. The first one, in this case, turns out to be just the class of the additive group of integers, and the first one is just vanish, is 0. But the second one is related with homomological multiplier, and in fact is given by the Potrier-Dual of this polynomial multiplier. And so, moreover, the proof is not hard. You can compute explicitly using resolution of singularities the first three invariants, E0, E1, and E2. So you can prove that, well, the Ekedal invariant. So this is the homology of the class of the Ekedal invariant of EG. But EG can be write down as the limit of this series, but by the continuity of this H, and it turns out that you can stop at some point, and in fact you can compute the homological Ekedal invariant by taking a large enough M. So if you fix this M, then you can choose some very big M in such a way that the homological Ekedal invariant is given by this, by the homology of this thing. Okay, so on the other hand, you can also take resolution of singularities of this quotient variety in order to write down the class of the quotient variety as the sum of the classes of some smooth and Frother varieties. But moreover, you can do this in such a way that this X is birational to the quotient variety, and all these pieces are of lower dimension. And using this fact and Poincaré duality in order to compare, well, Poincaré duality and universal coefficient theorem in order to compare the torsion parts of these cohomology groups, Ekedal show this, well, Ekedal prove this theorem using this kind of explicit computation, let's say. Okay, so in fact this depends strongly on the fact that this quotient variety is irrational, and this is used, well, this is, you use this fact in order to show that this is simply connected, and then well, for instance, this vanish, and this allows you to compute the second one in terms of the torsion part of H2, which is just the Brodel group. So this is the Brodel group of X, which turns out to be equivalent to the unramified Brodel group of the quotient variety. Okay. So this is the idea of Ekedal's proof. And my goal in this talk, or the goal, or the kind of question that we are asking ourselves is if you can generalize Ekedal's result in some way. So we are trying to generalize Ekedal's result in two directions. The first one is kind of straightforward, so you can, of course, ask how, or if you can define something like the Ekedal invariant not for a finite group, which correspond to the classifying stack BG, but if you can define the Ekedal invariant of a general minimum for a stack. So this can be done, of course, in a straightforward manner. So you can start with some minimum for stack X, defined over this field, this base field K, and then you can take the class of the minimum for a stack in the class in the Grothendieck ring of stacks, and then you can push this to the motivic value ring through Ekedal's map, and this will produce, of course, some element in the completed motivic ring. Okay, so you can also try to compute explicitly how this Ekedal invariant of the minimum for a stack in terms of the classes of some varieties. So the analogous construction for a general minimum for a stack can be done in the following manner. So if you have a finite group and the corresponding classifying stack, then taking a faithful finite dimensional representation can be generalized in this setting if you take not a single representation, but you take a vector bundle over this X. So you can start with this X, and then you can try to find some vector bundle over this X in such a way that this vector bundle is in some sense faithful, like in the case of a representation of a finite group. So the corresponding condition for this E, which is a vector bundle over X, faithful in some way is that when you take the corresponding frame bundle of this vector bundle, then the total space of the frame bundle is so the total space of the frame bundle for some vector bundle over X is in principle just the minimum for a stack. But if you ask for a bundle such that its space of frames is not just a minimum for a stack, but a variety, that is the minimum for a stack without automorphisms for points, then this is the analogous notion for faithfulness in this case. So in fact, you can prove that this condition of being faithful in this sense is equivalent to that to the condition which says that if you take any point on X, then you have so when you have a vector bundle over a minimum for a stack, you can take a point in this minimum for a stack, and you can take the fiber over that point given by the vector model. So you can take the corresponding fiber, and this will produce a representation of the automorphism group of the point in the fiber, which is a linear space. So you get a local linear representation for each automorphism group. And if you ask that these local linear representations are faithful, that is, the automorphism group injects into the general linear group of the fiber, then this is equivalent to say that the frame bundle is not just a minimum for a stack, but a variety. Okay, so of course, this is not always the case for any minimum for a stack. So an arbitrary minimum for a stack, it is not true that an arbitrary minimum for a stack has a vector bundle like this. And in fact, this condition of having such a vector bundle is closely related with the presentability of the stack as a global quotient of this form. So if you ask that the minimum for a stack has enough vector bundles, then you can always find such a vector bundle in such a way that the frame bundle becomes a manifold, a variety. And this condition is also equivalent to the resolution property for varieties or for stacks, which says that whenever you have a Kochelian sheaf over X, then the Kochelian sheaf is the quotient of some vector bundle. So this is the resolution property, and if this X satisfies the resolution property, then it turns out that there exists some faithful vector bundle. Okay, so once you write down this X in this form, like a global quotient like this, then of course you can compute the class of X using this kind of presentation, and this turns out to be equivalent to this, or identical to this element. So you take the class of the frame bundle, which is assumed to be a variety, and then you can divide by the class of GLN, and this is and you can write down the class, the Ekedal invariant in the rotative ring of varieties, like that, in terms of varieties. Okay, so now you can also do something similar as in the case of finite groups. So you can start with this faithful vector bundle, and you can also consider the corresponding direct sum of this vector bundle n times. Well, I will denote by E sub m as the class, as the first modular space of the total bundle space of this E to the m, and this is the analog of taking B to the m divided by G. So this is just the same. And you have an analogous proposition as Ekedal's in this global context. So you can also take the corresponding limit in the monotypic value ring by taking these kind of normalizations, and this will produce, you can compute also the Ekedal invariant of X in terms of varieties, just like that. Okay, so of course, you also have these the corresponding cohomological invariance, because you have defined this h to the n on the whole completed motivic ring, so you can just take the cohomology of this EG, which lives there, and this will produce some a whole series of cohomological equidal invariants. Okay, so the question will be if something similar happens in this global context for E2. So we know that E2 of BG is the Bogomolov multiplier of G. So you can ask if there is some relation of this E2 for a general, the link for a stack, if you assume, let's say, if X is smooth, maybe, if there is some relation between this E2 and the Brauer group of X in this general. Okay, so the point is that you can prove something like that, but Ekedal's method is a little bit hard to generalize in this setting. So Ekedal's method use this resolution on singularities and use the fact that this, in that case, the quotient variety is irrational in order to compute some the first invariants. But if you try to push this method in general, what you get is, or what you can get is something like that. So the first part is trivial, so all the equidal invariants vanish for negative indices. And well, of course, the first one is related with the set of connected components of this X. In the previous case, then this has just one connected component. This is just the class of C. The second one vanished in the case of a finite group, but for an arbitrary, let's say, smooth, the link for a stack which satisfies the resolution property, then what you expect is that the first equidal invariant is given by P naught of X like that. And the idea is just using the very same procedure, using resolution on singularities, and compare this and compare homology groups using Poincaré duality and the universal coefficient theorem. So you can do that in that case in order to prove this thing, and this will also allows you to compute maybe the second equidal invariant in terms of the Brauer group of X, if you assume that X is smooth, for instance. Okay, so of course you can ask what about the higher order equidal invariants, and you can try to think how these higher order invariants can be written down in some way. So let me just conclude by some very naive speculations that we are trying to pursue regarding possible realization of these higher equidal invariants in terms of some kind of higher Brauer group. So if you know the first three equidal invariants are related, so know that this is P naught of X, this is the Brauer group. The first one is related with, well, the second one is related with the Brauer group, and the Brauer group classifies torsion jerks over X. So in some way you can think that E1, which is P naught of X, classifies. So this can be thought as a group which classifies torsion 1 jerks over X, and this can be thought of as a group which classifies torsion 0 jerks over X. And so you may ask if something similar happens for higher values of n. So a question will be if, well, you know that these three, for 0, 1, and 2, this is related with torsion years of the corresponding degree or order. So you can ask if something similar happens for higher values, in the sense that you can try to produce some group which classify like the Brauer group, not one torsion 1 years, but you can try to produce some group which classify torsion n years, higher order years, in such a way that these groups are probably related with higher equidal invariance in this way. So of course there are some possibilities to do something like that. So for instance, 1 year torsion years are classified by Asumaya algebras, and there exists some higher other notions of Asumaya algebras in the context of derived algebraic geometry, for instance. So there is this notion of derived Asumaya algebra and the corresponding Brauer spaces, whose homotopy groups are related with this, should be related with these higher torsion years. And so, well, if you can define higher Brauer groups in such a way that such higher Brauer groups classify higher torsion years, then you can try to compare these classes with the classes of the corresponding equidal invariance at the same level, and you can try to show if these two agree or not. So this would be some speculations about these two things. So, for instance, if you try to do something like that using equidals method, by taking resolution of singularities, this seems to be hopeless, maybe. So you cannot just proceed like that by means of a direct computation. So you can try to perhaps proceed in a more conceptual way, maybe with this, maybe taking some kind of inductive process by considering now the loop spaces of the free loop space of X in the sense that you can consider, so in this derived setting you have this derived loop space, so you can try to compare n ordered years with n minus 1 ordered years using the derived loop space, and maybe you can try to find some inductive process which allows you to start with the Brauer group and then go up to the higher order ones like this. So I think that this is all I want to say. Thank you.
Questions? Well, thank you very much. We'll continue at 2:30. Now lunch is much